review or definition in the section spectrum. Let A be a unitary algebra and let A be an element of A. The resultant set of A is this set, rho A of A equal to the set of all complex numbers such that Z multiplied by EA minus A be an invertible element of A. This is the resultant set of A. And the spectrum of A, denoted by this, is the complement of rho A, so that sigma A of A equal to the completion of rho A of A with respect to complex plan. The resultant function of A is this function Ra that maps Z to the inverse of this element of A, because if this Z belongs to the resultant set, we know that this is invertible, so that the inverse of this element exists in A, and this function is well defined. And we see that we have this equality. Now suppose that A is a Banach algebra and let A belong to A. It follows from this theorem that sigma A is a subset of this ball, this unit ball. Not unit ball, this ball, because this may be greater than 1. And we have the definition: let A be a unitary algebra and A belong to A. The spectral radius of A, denoted by this or this, defined by this supremum. The supremum of all absolute value complex numbers such that this belongs to the spectrum of A. This is called the spectral radius of A. And the element A is quasi-nilpotent if nu of A equal to 0 or sigma A equal to 0 or empty set. If the spectral radius of A equal to 0, then we say that A is a quasi-nilpotent element. The set of all quasi-nilpotents is denoted by Q of A. The set of all quasi-nilpotent theorem. Okay? And finally, we see this proposition that we prove two first items by this proposition. Let A be a unitary Banach algebra and A belong to A. Then the resultant set rho A is open in C. This is an open subset. And 2, for each lambda in the dual of A, this function lambda or the resultant function is analytic on rho of A. Okay? That we prove these two theorem, lambda O F. And this is the proof of 2. Now we want proof another items. For 3, we know that by I, the spectrum sigma A is closed, because in the first part we proved that row of A is open, so that its complement must be closed, okay? Because sigma of A is the complement of row of A, okay? This is must be closed. And we know that this is bounded, because we see that this set is a subset of the set of all elements in A with norm less than or equal the norm of A, okay? To prove this for you, sigma A is the subset of this, so that this set is bounded, and also this is closed, so this set must be compact. Please note that by the Heine-Borel theorem, if A be a subset of Rn such that A is closed and A is bounded, then A must be compact. For any subset of Rn, if A is closed and bounded, then A must be compact. This is my theory, okay? But it makes compact space is bounded and closed, so that we have this equality. But Heine-Borel proved that for subsets of Rn, okay, Euclidean space, if A is closed and bounded, then A must be compact. So sigma A is closed and bounded, so must be compact by the Heine-Borel theorem. Heine-Borel theorem. Assume toward a contradiction that sigma A be empty set. We want to prove that this is non-empty set, okay? Because if we assume that the spectrum of A is empty set, then for any element in the dual of A, for any lambda in A prime, by 2 we know that this function is entire. Entire is meaning that this is analytic in whole of C. We prove this for you. Okay? We prove the definition of entire function in the previous session. A complex value function that is holomorphism or analytic on the whole of complex plan is called entire function. Okay? Entire function. But are A of Z equal to this? If we multiple the inverse of Z to this, we see that this is equal to Z E minus A. Okay, Z E minus A. And so that this tends to 0. If the absolute value of Z tends to the infinity, because we have the inverse of Z. Let me write or recall this for you. This is our resultant function. ZEA minus A. And let me write is 2 for you. Three. Sigma of A is closed and bounded by 1 and a star. For example, if we denoted this by a star. This is a star. Okay? A star. So sigma of A is compact by the Heine-Borel theorem. Now, if lambda belong to this set, for example, Okay. If sigma A equal to 0, let me write this for you. If sigma A equal to the empty set, then row A is equal to the whole of complex number, because we know that these two are the complement of each other. Then this is equal to C. So that for any Z in complex numbers, ZEA minus A is an invertible element of A. Okay? Because any complex number must be belong to row of A. So that any Z in C must have this property. ZE minus A is an invertible element. Okay? But RA of Z equal to ZEA minus A inverse. And this is equal to Z inverse EA minus the inverse of A. And we can write this Z inverse multiplied by EA minus this set, okay, or this element. And this is equal to we can write this the inverse of Z multiplied by EA minus the inverse of Z multiplied by 8, then inverse. Okay, the inverse of this element is this. It's very trivial. So the norm of RA of Z equal to the norm of this element and this is less than or equal this multiplied by the norm of this. And this is 2, 0 if this tends to infinity. Because the absolute value of element is 1 divided by the absolute value of z, okay? The absolute value of z. This shows that this function must be bounded, and so by the Liouville's theorem this function must be 0. Let me recall again the Liouville theorem. Let f be an entire and bounded, then f must be constant. Okay? In our proposition, we can write therefore for any lambda, for example, in the dual of A, lambda of O or A is a entire and bounded function. Bounded function and so by the Liouville theorem must become this function must be constant. But it is trivial that if we consider z equal to 0, this is equal to the identity map, and so lambda O this must be equal to 0, so that all of this must be equal to 0. Okay, this shows that this function at 0 equal to 0. This is true for each lambda, so that this must be equal to 0. So that since this tends to 0, this must be equal to 0 because this is continuous. So for each lambda in the dual of A, lambda of RA of 0 must be equal to 0 for each lambda, and so this must be 0. This must be 0 by the Han-Banach theorem. But this is a contradiction. Let me write. By the Han-Banach theorem, it is trivial because RA of 0 equal to 0 E minus A inverse, and this is equal to the inverse of A, and this is a non-zero element. Okay, this is a non-zero element. Okay, so this is must be a non-empty set. This contradiction shows that it must be a non-empty set. And finally, for the part 4, for each n and for each r greater than the spectral radius of A, we have this equality. We see that for each radius greater than the norm of A, this series is uniformly convergent. Okay, this series is a uniformly convergent series. Because if you consider, let me write A K Z K plus 1. Okay, for any this is for if all be created then known as A. Okay. Then this series converge uniformly is a convergent series because for each j equal to 0, 1, 2 up to the end, we see that the norm of equal to the absolute value of the car and this is less than or equal this multiplied by r to the power of k by this equality, okay, and this is strictly okay. But if z belong to this set, this is equal to 1. So if you consider k to this set and also for each k in this set and for each z in this set. Okay, the ball with radius r. This equal to r. We have these inequalities. Let me write. Is not equal to r. Okay, we have this. So this is a convergence series, and also we have this series. Please note that since this is convergence, this is a convergence series, because let me write this. This must be convergence. Because this is equal to this multiplied by this. Okay. Okay, since this is a convergence, this must be convergence. Also we have this is convergence. Okay, now moreover we have this series converges to the inverse of this element, Ze minus A inverse. This is very easy to check. Let me prove this, that this series multiplied by this, okay, and this multiplied by this series equal to the identity element of A. We write some similar equalities in the previous sessions. You can check this easily, so that this is the inverse of this and this is the inverse of this, and you can prove this equality. And so the equation holds for this value of R. So if we consider the set of, we consider R greater than this node, we have this equality. Because in 4 we must prove this. But if R be greater than sigma A, since this is an analytic function on rho of A, the equation holds for all R greater than the spectral radius by the Cauchy's theorem. This Cauchy's theorem, I think I don't recall this for you in the next session. Okay. Okay. Let me recall this for you in the next session, okay? If RB greater than sigma A, then the equality is held by the Cauchy's theorem that we write the Cauchy's theorem in the next session for you, okay? Dear students, Ma salam, thank you, goodbye.